Hi guys, today we're learning about moles.
Who do y'all want to learn from, me or the little one? She's really good, and we wear the same color, apparently. So, thank you, baby. Hi, everybody. It's me again. Lecture 2 of the unit is mole fractions and the ideal gas law. Mole fractions is new, ideal gas law is totally not. So that's good news. So make sure you have your slides out from off of Schoology. You will need your periodic table, calculator, spiral. So have all of that in front of you. Pause if you don't have it, and we are going to we're going to jump right in. So I can't not show you that. So now we feel good about, yay, it's AP chemistry. All right, so here we go.
Mr. C, this class is so boring.
And that's the other daughter who's loving the video. That was the, okay, I love it. Here, say hi to the people.
So boring.
Okay. Okay, anyway, no more interruptions, maybe. All right, go here. Okay, so mole fractions. It's exactly what it sounds like. It's going to be the ratio of the number of moles of one component of the mixture to the total moles of all components of the mixture. So if we were going to do something real simple in coming up with a mole ratio of the gases that are in the room, again, last lecture we used oxygen, nitrogen, and carbon dioxide as just the three most common ones. So with that said, if I wanted to find the mole ratio of one of those, let's say carbon dioxide, we would say, all right, well, we're going to go X of CO2 because this X is always going to represent the mole ratio, or the mole fraction, I'm sorry. So just have that in your memory. But again, if we're going to do the mole ratio of, the mole fraction, my apologies, of carbon dioxide, we would need to say, okay, well, we need to know the moles of carbon dioxide, and that would be over all of the gases, all right, which in this case, from our example, would be the moles of O2, that's going to be added to the moles of N2, which would be added to the moles of CO2. And now we would have the part over the whole setting up the mole fraction. All right, and then we would put values in there and we can actually assign the different numbers. This whole idea of mole fractions is actually derived from Dalton's law, which is why it fits really good in this spot since we just finished talking about Dalton's law in the last lecture. But the other reason that these proportions work the way we do is because of Avogadro's law, which is something we covered last year, which is a focus of moles. Avogadro's law simply states that at the same temperature, pressure, and volume, that gas will have a constant number of moles compared to any other gas, as long as it's at that temperature, pressure, and volume. Jarvis, stop it. Terrorizing the cats. Remember, you met all the animals in the last video. Go back if you missed out on that. Anyway, so that's our basic idea of what we're starting off with, is how to calculate these mole fractions based on some situations. Now, in terms of actually calculating, these are the two equations that will be most helpful for solving a problem. So just a couple things, like in the equation you just saw, the PTOT is the total pressure of the system, whereas the capital P with whatever gas it is going to be the partial pressure. And then, of course, we now know that the X is going to be referring to the mole fraction itself. So did you have something to say? Okay. So anyway, we can put those equations into action in a couple of problems here. So I'll have these pulled up for you. All right, so taking a look at the first one, just by identifying what the unknown is, it would help assign which of the equations associated with finding mole fractions that you would want to use. So as I look at the first one, it says calculate the partial pressure. All right, well, right away, if I'm calculating partial pressure, that's the equation that takes the partial pressure and allows you to solve for it, which is going to be my PA is going to equal the mole fraction, which is going to be multiplied by my total pressure. All right, so now it just becomes plug and chug, which I don't anticipate you'll have much trouble with. So as I read number one, it says flat out that the mole fraction of nitrogen in the air is being referred to as 0.7808. So there's my mole fraction. So if I'm going to solve here, all right, we're going to be 0.7808 there, multiplied by a total pressure. And if we read the problem, it lets you know that the total pressure of this system is 760 torr. Oops. All right, and now we're able to, oh, there's a decimal there. All right, and now you're able to simply solve. All right, and in this case, the partial pressure of the nitrogen that it's wanting us to find is going to come out to 593 torr. Take a stab at the second one, pause the video. It's another plug and chug, so you should have no issues whatsoever. All right, so it wants us to find the mole fraction. So right away with the phrase mole fraction, I know that it's the X that needs to be isolated. In order to find the mole fraction, we must divide the partial pressure by the total pressure. So there's the equation that we'll be following. And again, the numbers are easily identifiable in the problem. So it lets us know right away that my partial pressure of the oxygen is 156 torr. So now we're at 156 divided by my total pressure. It lets you know the atmospheric pressure here is 743. So we've got our problem set up there. Now I do want to point out that our mole fractions do not have units. You'll notice that in the previous problem, there is no unit written there, so you're not expected to report a unit of any kind. So as I get a final answer here, I'm going to get 0.210. All right, anybody remember the cool way we say the ideal gas law equation? That's right, it's PIV-NERT. So if you want to be cool and fit in with all the awesome kids, PIV-NERT's the way to go. Y'all want to come say PIV-NERT? Here, come say PIV-NERT for the camera.
PIV-NERT.
Perfect, nailed it. Sky?
I'm awesome.
Oh, well, now you're out of your shell. Nice. Okay. This is here. So here's some of the basic information that we need to make sure that we know for the ideal gas law. This is on your AP sheet, so you'll be able to look it up and use it. So N is moles here. The important thing here is to be aware of your R value. We're going to be using 0.0821. There's many disciplines that use the 0.08206 as the longer constant value, but whatever. It's the units of the R value that are going to dictate all the other units that must go into this equation. So we're dealing with liters, atmospheres, moles, and Kelvin. Must be the 4 units that are associated with everybody else. So if you look back at the R value, you'll see that there's no guesswork there. If you run into a problem that most commonly is using the wrong pressure units, get converted to the correct pressure. Of course, degrees Celsius is never okay, but if you're given milliliters, that's also no bueno. turn it to liters. So just be aware that the R value here is dictating the units of everything else. I do want to mention that while we are diving into the ideal gas law here, that the difference between the combined and the ideal, I may have already said it, but the combined gas law that we studied in the previous lecture is a reaction to a change in the system. We've got the system and we say, okay, well now the pressure's been altered to this, and it makes the other stuff change. The ideal gas law doesn't look at it like that. There are no P1s and P2s, right? If you look at the equation, it's just a set of variables, because what we're doing is a snapshot of a gas system, not changing anything, just looking as it exists in a given setting under certain parameters. All right, so we've got some values here. One of the ways that I know that we're dealing with the ideal gas law is that there's no repeat in units, so that kind of helps out. So what I can do though is I can just start identifying stuff. All right, it looks like it gives me 0.0460 moles as one of the given numbers, and then 33 degrees Celsius. All right, followed by 9.50 liters. All right, so there's a couple issues in there that we need to be aware of. First off, the 33 degrees Celsius is no good. All right, so make sure that it turns into Kelvin while we work it out. Liters and moles are both good according to our R value. So we'll be good to start plugging and chugging here. So as we go into PIVNERT, all right, it looks like my pressure in this case is what we're looking for. All right, the volume is the 9.50. My mole count is 0.0460. All right, my R value, of course, is my 0.0821. And then my temperature, but in Kelvin, is going to be sitting at 306. Apparently, I'm writing too big. But anyhow, solve for X. All right, so it's going to spit out pressure, but of course we've looked at kPa and torr and millimeters of mercury. So keep in mind that whatever units go into any of these equations are the only units they're capable of producing. Therefore, it must be atmospheres. I get 1.22. All right, so that should be absolute review because we worked those problems out last year. What is going to be new, though, is finding, that's not funny. What is going to be new is finding gas density, which is going to be a new equation that will be super helpful to you, and it's not on the AP sheet. So this is going to be one that I'm going to recommend that you memorize. All right, so here's my slide for connecting both gas density with molar mass. Now, the way that I remember that equation, or the way that I was taught, is that the meow puts the dirt over its pee. That was crazy, right? But if you take a look, what you can do is if you flip over this second M here, all right, it would be a W, and that would make you think of meow. And then, of course, after your kitty goes pee-pee in its litter box, it pulls, has to put the dirt over its pee-pee. So anyway, the molar mass equals density times R times temperature over pressure is what we're looking at there. So let's put dirt over the cat's pee in a couple problems. So in my first question here, it's looking directly, for the density of a gas. I was going to get my wife to come do a cameo also, and she's standing right over there, but she's refusing to come be fun. So we'll have to continue to wonder if she even exists. Okay. But I can't tell some of my jokes because she's here. Anyway, okay. Calculate the density of oxygen at STP. Awesome. We're back to STP. Just get our equation on the board. We know that my meow, but I'm not going to flip the M around, is going to be my dirt over the P. And we're looking for the D density there. Now, what I notice about this problem is that we're dealing with oxygen. So what I know right away is that oxygen is O2. So I'm actually able to identify the value of molar mass right away here. So oxygen's got a mass of 16, so we can assume immediately that we are dealing with a molar mass of 32. All right, so we've got 32 over, we're looking for density, so that can be my X. My R value is 0.0821. All right, my temperature in the problem is STP, so right away we know it's going to be sticking at 273 Kelvin. All right, and I want to put all of that over the given pressure, which in this case is going to be my standard pressure. We want to keep it in atmospheres, so that is the number 1. Solve for X. So it's a density we're finding. Your slides remind you of the units of density, but anyhow, we're going to end up with 1.43 grams per liter. Now, while this type of question certainly does exist in AP, the next one is one that you see more common because it crisscrosses skills. So let's take a look at a slightly tougher gas density problem. Oh, dang, I didn't hit record. Come on. Oh, I almost got her. It almost worked. Oh, she gave me a look like I was stupid. Okay. Looking at the other problem on that slide, it says a compound has an empirical formula of CHCl. It gives you a volume flask that it's in at a temperature and a pressure, and then it also gives you the grams of the compound. Then it asks for the molecular formula. So what we're looking at here is a molecular empirical connection that we'll have to solve after we put the the meow puts the dirt on its pee-pee. They keep not hearing me say it, and they would think it was hilarious if they heard me say it. But anyway, okay. So here's what I know right away is that there's enough information in the problem to figure out density just using the density equation. We know in order to find density, it's grams over liters. So I can use that information right away. So I can take this 0.8 grams that it gives me another sig fig, all right? And I can divide that value by the given liters of 0.256. All right, notice I did a conversion there, all right, because it gave it in milliliters, which is no good for finding density. But I can use this equation to find my density of 3.1 grams per liters, all right, and that's going to be the D. So back to one of your simplest skills, how to find density. It's mass over volume. So now I've got one of the values that I'm going to need in order to continue. Now, looking at the given values back in the problem, you'll notice that there is a pressure issue because it gives you 750 torque. Because what we're going to do at this point is we're going to find the molar mass by plugging in all of these parts. However, the pressure that it gives me is torque, and the R value that we use requires atmospheres. So you need to do a conversion there of going from the, 750 torque into atmospheres, which if you do that conversion, 750 ultimately divided by 760, it's going to give you 0.99. So as I start looking at my values here, all right, I've got 0.99 atmospheres. I've got 3.1 grams per liter. We've got our temperature is sitting at 373 Kelvin. All right, and now we're able to plug in all of this information. So let's go ahead and plug and chug. All right, so in order to find the molar mass, it's going to be, we need to put dirt on the P. So let's take our D of 3.1, all right, times R of 0.0821. Times my temperature of 373. And all of that over my pressure of 0.99. So this is going to give us our molar mass of the sample, all right, which is going to be with sig figs 96 grams per mole. However, that's not what this question wants. It wants to know what is the molecular formula based off the empirical formula of CHCl. And here's where we need to remember how that part works. In order to find a molecular from an empirical, we very simply need to know the mass of the molecular, the mass of the empirical, and figure out how many times that empirical goes into the molecular. So, in other words, I'm out of space, so let's free up a little bit here. So in other words, what we're looking at doing is saying, okay, well, it's CHCl. CHCl. And here's where you would need your periodic table. If you look it up on the periodic table and add that compound up, you're going to get 48.47. 48.47 is the molar mass of the empirical formula. But now if I take the molar mass of this molecular formula, which is what we found using my problem, I can figure out how much I need to multiply the subscripts of this empirical by to get a final answer. So then what we would ultimately need to do is we would take the 96 that we got, divide it by the mass of the empirical. Whiteboard's going to break. All right, and here's where you'll always get a whole number. All right, sometimes it's like 0.9999 or 0.0001 or whatever, but in this case, you're going to get a whole number of 2. And this will now indicate the number that you need to multiply these subscripts by. So when it's all said and done, the final answer to the problem is going to be C2, H2, Cl2. The problem we're going to end with is a little bit of Pivner with gas stoichiometry. I don't think you'll have any problem with that. So let's just do one more of these. It's another real simple type of problem that you've seen before. Crosses 2 skills, but the most recent one I saw of this was an FRQ, one of the steps of a gas law FRQ. So we'll want to make sure that we are good at it. All right, so we have a balanced equation here. So of course, if I'm calling this gas stoichiometry, you're going to have an equation to use because the mole ratios will be vital for stoichiometry. But you can see that it's already balanced. We've got water reacting with iron in the equation. But then look at what it gives you. It wants you to calculate a volume of hydrogen that's going to form hydrogen gas at the end, which is one of the products of the reaction. But what it gives you is an amount of reactant. So it's only giving us the amount of one of the reactants, which makes me assume that I don't have to find a limiting reactant. We're going to have to assume that the other item is in excess. Actually, it's passing through the iron tube. So we're going to watch this reaction take place. But we need to know the moles of H2 to put into Pivnert. So it ultimately starts as a grams to mole stoichiometry problem to figure out, based on the amount of water that we're starting with, how much hydrogen will be created. So what I'll do then is I will start off with my, is it 40? 98, sorry. We'll start off with 98.3 grams of water, all right? And we're wanting to do stoichiometry to get this to moles of the product because, of course, my Pivnert has that mole spot for us to look at gases. So we can't start with grams though. So we want to go from grams of water to moles of water. All right. And then once we have moles of water, we can then find moles of our product, which in this case is H2. All right. We know in our dimensional analysis grids, the diagonals are going to match. All right. So now we can put in our values. We've got moles over grams here. We know for every 1 mole of water, it's going to have periodic table of the H2O, which is going to be 18.02 will be the mass there. And then here, when moles is over moles, it's always my, my mole ratio from the equation. So look back up to the balanced equation, find water, find H2, and you'll see in this case, they both have a coefficient of 4. All right, so tail was a little long over here. So now we can run the grid, multiply across the top, get a number, multiply across the bottom, get a number, divide the top by the bottom, and you're going to spit out 5.46 moles. Of H2. And now we know how many moles of product we're dealing with, and we can easily switch directly over to Pivnert and plug in all the values that we are now provided. So my pressure in this case is 0.98. That's in the problem. So we're going to go 0.98 is P. We now need a V. All right, so V is actually what's missing, which wants us to find the volume. So we will be solving for him. So PV equals nRT. My mole count is 5.46. My R is 0.0821. All right, and then my temperature, it gives it in Celsius. Make sure that you don't do that. It's going to be 723 Kelvin. The magic number is add 273 if that number has slipped your mind. We can now solve for that volume. I get 330 liters.